Hello, everyone. This is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics. And this lecture is going to be about the independent samples t-test. So, just a little quick review. T-tests in general are operating under the t-distribution. The t-distribution is different than the normal curve, right? So, with the normal curve, there's only one curve. It's called the standard normal distribution. With the t-distribution, you have a different distribution of t for every sample size. So when your sample changes, so does the curve. So as n, as your sample size goes to theoretically infinity, t will become z. Now, you are not going to be going to infinity as your sample size, right? That's just a theoretical thing to talk about. But as your n gets pretty large, like over 100, t and z are very close to each other. The biggest discrepancy you'll have is when you have a small sample, then t is going to be harder to reject the null. So t is underpowered. T has less power than z, statistical power. Statistical power is the ability to correctly reject the null hypothesis. So you want power in your sample that you're using because if the result is real, that means if the result is in the population, you want to find that same result in your sample. So you need higher power, usually 0.80 or above for power. The other issue with T is the estimation of the population standard deviation. For T, we do not know sigma, the population standard deviation. So it's very important. Also, for T, we are making one comparison only. So for the single sample, the one sample T, right? This is going to be a sample mean compared to the population mean. So you only have one comparison. That means you're only comparing two things, two groups, or two parameters or statistics to a population mean. So the one sample or the single sample t-test is a single sample mean compared to the, sorry about that. I got the population mean in the single sample test, t-test, represents the null hypothesis. This is the null hypothesis. That's for a single sample test. I have one sample and I'm comparing it to a population mean. In general, that mean is a historical parameter. Like, so you have lots of previous data on something, you have a historical average, a population mean, and you're comparing your sample to that historical average. With the independent samples T, we have a little bit of a different situation going on. So for independent samples T, we don't know sigma still. I mean, that's obvious for all t-tests. We don't know sigma, the population standard deviation. But this is a comparison of exactly two groups. Comparison of two independent groups. They are different people in each group. They are not related. They have no correlation. They're two different groups, right? It cannot be correlated. One of the big assumptions is when you're doing the independent groups t-test that the population variances that you pick the two samples out of, right? So independent groups are really samples, right? So these two samples, their population variance has to be relatively equal. And you can check that. And we did this in SPSS. You could also use Levene's test, right? Check with Levene's test. I'm not a big fan of Levene's test. Levene's test is overpowered, in my opinion. That means that it's too easy to reject the null using Levene's test if you have a bigger sample. And if you reject the null of Levene's test, you're saying that the population means are not equal. So the null for Levene's test is the population means are equal. Population variances, I'm sorry. So the population variances are equal. So sigma squared 1 is equal to sigma squared 2. That's the null, right? The alternative is that they're not equal. And that creates a problem, right? So you don't want to reject the null for Levene's test. So you don't want to. So this is the rare situation where you don't want to reject null when you're using Levene's test, because then you have to deal with the variances not being equal. And if they're not equal, there is a penalty. So you lose power, right? So that's the reason why I don't really care for Levene's test, because it's too easy to reject the null. You lose statistical power when you assume that these are not equal, that the variances are published variances are not equal. So we don't want that. We want to not reject the null with Levene's test. Still, Levene's test is a problem, especially with bigger sample sizes. It's too easy to reject the null. So you can also do the rule of thumb I gave. The largest variance must be no more should be no more than 4 times the smallest. And you only have 2 estimates, right? You have a sample variance from group 1 and you have a sample variance from group 2, and you got to compare them. The largest variance should be no more than 4. So if that's the case, then we fail to reject the null, which is what we want here, right? We want to fail to reject the null because the null says the variances are equal. So this is what we want, right? That's why I use this rule of thumb. The largest variance should be no more than 4 times the smaller. If that's the case, you're going to not reject the null, and you're going to say that the population variances are equal. If the largest variance is more than 4 times the smallest, then you're going to reject the null, and you're going to say it's not equal. Now, if you reject the null and you say that the variances are not equal, you need SPSS or another statistical program to find you the alternate degrees of freedom that are going to be used to test the hypothesis. So, in other words, it makes your life a mess and you lose power. So, you don't want this. So, you want to make sure that there's no extreme difference in variances between the 2 groups before you even consider, altering the t-test that you're doing and making it harder. Otherwise, you're going to make it hard to reject the null if you decide to to say the variances are not equal, rejecting an adult becomes harder. So that's important as well, right? You also don't want any heavy skewness in the data. So that's important that the data is not skewed and the data have to be independent. Like I said before, they cannot be related. So the two groups cannot be related. Two samples are independent. We need to make sure that's the case, right? They should not be highly correlated with each other, group 1 and group 2. So this is low correlation between those groups. And you also you do not want strange things going on like extreme skewness or non-normality, right? So if it doesn't look like it's distributed according to like a normal distribution, if it's way off, then you're gonna have a problem with the t-test. However, the t-test in all its forms is robust against violations of these assumptions. That means you have to have a real extreme amount of different variances or skewness or something else, right? These are what are called assumptions. So the t-test is robust, which means it's not going to be really affected unless you have extreme unequalness in variances or extreme skewness or extreme non-normality, right? Or a very high correlation between the two data sets. So it tolerates most of this very well, but you can have situations where it's difficult to run the t-test if you have a really messy data set. Most of the time, it's not the case because even if you have a small sample, you could probably get away with using the t-test. But if your sample is small and a mess and looks really, the distribution is really off, then you're probably not going to want to run that. You're going to probably want to run the non-parametric test like the sign test or the binomial test, which I showed you earlier. So these are just some other things you need to know. So independent groups t-test, two samples that are independent of each other, and we're going to compare those samples. So the null is always going to be no change or difference between the groups, right? So in other words, the mean of the first group is going to be relatively equal to the mean of the second group. Doesn't have to be exactly equal, but somewhat equal, right? And the alternative is going to be the change. Change would be non-directional, right? Or an increase, decrease. Right, this would be directional. So you'd be able to identify whether it's non-directional or directional. So that's basically how it's set up. Right. So let's go through. Let's go to degrees of freedom first. The degrees of freedom for the independent groups t-test, the two sample t, is equal to big N. This is the total sample size minus 2. Or sometimes you see it written as N1 minus 1. So this is big capital N is the total sample size, right? Minus 2. Or you can see it written as sample 1 minus 1 plus sample 2 minus 1, which then turns into N1, right? Plus N2 minus 2. So you may see it written like this as well. But it's basically your total sample size, the number of people total in both groups combined, minus 2, which is the same as this. Right? It's just ways of writing it. Why is that a minus 2? Because we're estimating two parameters. We're estimating the population variance for sample 1, and then we're estimating the population variance for sample 2. So since we're estimating two population variances, we lose 2 degrees of freedom. Before, we were only estimating one sample population variance because we had one sample. Here we have two samples, so we're estimating two independent samples, that is. Now I'm going to give you the formulas first, and then we're going to walk through a couple problems here. So for independent groups design, we have two samples, therefore we have two variance estimates. We have the variance estimate for sample 1, and we have the variance estimate for sample 2, because we have a total of 2. Right. So we have those two variance estimates. We lose those 2 degrees of freedom. But since we have two independent estimates of the variability of the variance, we have to decide how do we take those two independent estimates of variance and transform it to one estimate of variance that we're going to work with, right? And so they've come up with, I don't know, whoever designed the t-test, and that was wonder whoever the Tukey, not Tukey. Was it Tukey? No, student. No, so the student T. There was someone that basically gave the pen name as student when they developed the t-test. So it's always called student's t-test for whatever reason. So with the student's t, we have to come up with an estimate of variance. So we're going to use something called the pooled variance estimate. So what the pooled variance estimate is, it takes both of your sample variances, the sample variance for group 1 and the sample variance for group 2, and it comes with a combination measure of it. It combines them. So this is calculated. It's written as S squared sub P. Sub P means pooled. S squared is variance, sample variance. S squared sub P is equal to the sum of squares for group 1 plus the sum of squares for group 2 over degrees of freedom for group 1 plus the degrees of freedom for group 2. So we have to actually calculate the sum of squares for both samples and the degrees of freedom for both samples, plug it in, and we get the pooled variance estimate. Then we're going to use that pooled variance estimate to compute our t statistic. So mean 1 minus mean 2 on the top, so the difference of the two means. And on the bottom, square root, pooled variance estimate divided by the sample size of group 1 plus pooled variance estimate divided by the sample size of group 2. And that's going to be your formula for independent groups. This is independent groups T. So you have to first find the pooled variance estimate, which is kind of a combined estimate of the two sample variances. And then we use that pooled variance into the denominator to find, this is still the standard error, right? It's S over radical N. It's just written differently. But this technically is still the standard error, and it's called the standard error of the difference between sample means, basically. You may see this independent groups T also being referred to as between subjects design or between subjects T. So you see independent groups or between groups or between subjects. They're used interchangeably. Let's move up and let's look at a problem. So I've taken these problems from the worksheets that I've posted for you on Brightspace. So I'm just pulling the problems right out of that. I already wrote those problems up and I already posted them for you. So in this first problem, let's take a look at it. The physiologist has conducted an experiment to see if hormone X increases sexual behavior in rats. 10 rats were injected with hormone X and 10 other rats received a placebo. So there are different rats in each group, therefore it's independent groups design. The number of meetings is the dependent variable over 20 minutes. So these are the number of meetings over 20 minutes. Okay, let's go back to our whiteboard. So first we're going to find the null and the alternative here. So I just copied it over here for us to look at. If I can get this to format correctly. So let me grab the data now. So I might be able to select this as a, no, it looks like I can't. Yeah, that didn't format well at all. All right, well, I tried to copy and paste it, but it's not working out. So I'm gonna have to write it out. It's just because I made a table. Maybe I shouldn't have made the table. I did. Just makes my life harder. Or we zoomed in too much here. So let's try to write hormone X. And then we also have placebo here. And we have 10 observations in each, 10 rats in each. And here's our data. Sloppily written by myself. And we have placebo. And these are matings within a 20-minute period. Now it looks like we're looking for an increase here. So it's going to be directional hypothesis. So we're going to have a directional hypothesis. Our null is going to be hormone X has no effect. That's has, by the way. Has no effect on rat mating behavior. And the alternative is directional because we think the drug is going to increase. So we're going to say hormone X increases directional term rat mating behavior. So we have a directional alternative hypothesis. And so now we're going to carry out the analysis by finding the pooled variance estimate, S squared sub P. So we have to do that first by finding the means of the two groups. So when I sum up this column, which is X1, we get 80. And when I sum up this column, the placebo column, which is X2, we get 60. And we know that N1 is 2, it's 10. Sample size of 1 is 10. Sample size of 2 is 10. And therefore, the degrees of freedom of each one is just N minus 1. So both of these degrees of freedom are 9. When I add them up, my total degrees of freedom is 18, which is N minus 2. 20 minus 2 is 18. Finding the means of these two groups. So the mean of hormone X is going to be 80 over 10, which is 8. And then the mean of the placebo is going to be 60 over 10, which is 6. So now I got the means. I got the degrees of freedom. I got the sample sizes. I need to find the variances. So we're going to do deviation score method because our means are whole numbers. So let's do deviation score method. So I'm going to write the deviation scores next to the values, the original values. So 8 is the mean for the first one. So I'm writing these deviation scores. What I'm doing is I'm subtracting 8 from each of these scores. Subtract 8 from all the scores in this first column. Got to subtract 8 from everything. Now this column should add up to 0. 2, 4 is 6. Minus 2 is 4. Minus 2 is 2. Minus 1 is 1. Plus 1 is 2. Minus 1 is 1. Minus 1 is 0. So it adds up to 0. And now I'm going to square these. These are the deviation scores. I'm going to square them to get the square deviation scores, just like we did with variance. And we keep doing it again and again and again. These are my square deviation scores, right? This is my x1 minus m1 squared. This is just simply x1 minus m1, right? Add up this column of square deviations and I get 20, 24, 28, 29, 30, 31, 32. So this 32 is my sum of squares for group 1. So the sum of that square deviation score column is your sum of squares for group 1. And now we got to do that with placebo here. Find the mean for the second group, which is 6. Subtract 6 from each of these. Subtract 6 from each of these scores. Make sure this adds up to 0. -4, -6, -5, -3, -4, -3, 0. And now square these deviation scores to get the sum of the square deviation scores, the sum of squares column. And I add up that column. And that's going to be sum of squares 2. So this is x2 minus mean 2 squared. The sum of the square deviation scores. 10, 14, 15, 19, 20, 21, 30. That 30 is my second sum of squares. So my first sum of squares is 32. My second sum of squares is 30. And now we can plug it into our formula and calculate the pooled variance estimate. So let's find the pooled variance estimate here. So S squared sub p pooled variance. This is equal to sum of squares 1 plus sum of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2. So basically, this is weighting both samples. So if you have one sample that's bigger than the other in the two sample test, it weights each column depending on the sample size. So it's a real even split between both groups. Here we have the same sample size, so it's basically a straight out average between these two groups. But if they have unequal sample sizes, it's going to weight the bigger samples more than the smaller sample. So we're going to plug in our sum of squares here. So 32 for sum of squares 1, 30 for sum of squares 2, and the degrees of freedom for each of these is n minus 1. So this is 9 plus 9. This gives me 62 over 18, which is equal to 3.44. That is my pooled variance estimate. Now that I have this, I can calculate T. So T is equal to mean 1 minus mean 2, mean of group 1 minus the mean of group 2, divided by the square root of the pooled variance estimate over N1 plus the pooled variance estimate over N2. Sample size 1, sample size 2. So we have our two means. 8 minus 6 goes on the top. The bottom becomes the square root of 3.44 over 10 plus 3.44 over 10 again. That weights the two sample sizes. So the top becomes 2, the bottom becomes, this is a common denominator, so I can add it, the square root of 6.88 over 10, or I could add the fractions over a common denominator. Simplifying this gives me 2 over, move the decimal point, square root of 0.688, which then gives me 2.41. That is my t value. It's not bad. It's over 2, which is good. Is it a no-brainer to reject the null here? No, we have to find the critical values first. So what are the critical values from the table that we can compare to 2.41? So we need to find the table. We know our degrees of freedom total is 18. And we are looking at points. So alpha here is 0.05. And our degrees of freedom here are 18. And this is also a one-tailed test. So it's a directional hypothesis. So since it's a directional hypothesis, it is a one-tailed test. And the one-tailed test gives you a little bit more power than the two-tailed tests. So there's a possibility we can reject the null here. What we have to do is go into our table, which is under study guide. So if we go into our study guide here, just find the table. So I'm going into course materials, and I'm going into study guides. And if you scroll down, you'll see study guide for exam 2 here, which is good to look at because you'll be having exam 2 a few weeks down the road. And then you have this Psych 220 formula sheet and tables exam 2. So we're going to want this formula sheet and tables exam 2 opened. And that gives me the formulas, which I already wrote down. But it also gives me the table, the T table. So we're going to look at this T table. We want 0.05 one-tailed. So go to the top row that says proportion of one tail. We'll find 0.05 in the top row and go down to our degrees of freedom, which are 18. And we have 1.734. Now, this is a positive critical value because we expect an increase of sexual behavior in rats. So we're going to be looking in the right tail, and therefore we want a positive critical value of 1.734. So our critical T is equal to 1.734. Now we compare our obtained T to our crit T. You can even draw the curve if you want. It's not a really great curve here, but we know zero's in the middle. We know that 1.734 is approximately here. We know that 2.41 is in the tail, right? So since our obtained value is more extreme than our critical value, because 2.41 is more extreme than 1.734, since our obtained value is more extreme than our critical value, we are going to reject the null. And when we reject the null, we conclude that the hormone X increases sexual behavior in rats. And that is our first problem we tested. Drug versus control, similar to a pharmaceutical study on a very small scale. You know, when you're testing drug versus placebo. That's what we're doing here. Reject the null for that. So let's try a different one. So I'm just going to clear this out here. And I'm going to want to copy and paste the new problem in here. So here's the big problem, a longer problem. Researchers at a leading university think that sleep affects memory consolidation. 24 memory consolidation is memory strengthening. 24 students volunteer from an introductory psych course were randomly assigned to either a sleep or no sleep group, and there were 12 participants in each group. On the first day, all students were flashed pictures of 15 different objects for 200 milliseconds each and on a computer screen and asked to remember as many of the objects as possible. That night, the sleep group got an ordinary night's sleep. The no sleep group was kept awake until the second night. All subjects got an ordinary night's sleep on the second and third night. On the fourth day, all subjects were asked and tested on how many of the original 15 objects they remember. So basically, they're testing a hypothesis that that initial sleep following the memory task is what's important, and that's what consolidates the memory, right? So now their hypothesis is not that this no sleep group will do worse than the sleep group. Their hypothesis is that there'll be a difference. Sleep affects memory consolidation, right? So sleep affects right here, that means that basically you're not giving a direction. You're not saying that sleep improves memory. You're saying sleep affects memory. So we're using a two-tailed test here. So let's write out the two hypotheses. Our null is going to be that sleep has no effect on memory. And then our alternative is two-tailed, that sleep has an effect on memory. So you're not putting a directional term in there because we're going to look for any kind of change. We're going to look in the positive tail and the negative tail of the distribution. So sleep has an effect on memory. Now we're going to look at the data. So we have a sleep group and we have a non-sleep group. So I'm going to call that sleep. And then we're also going to have non-sleep, right? Or no sleep. And here are the data for the sleep group. And out of 15, remember there were 15 pictures or objects, and they were tested on memory recall of those 15. So these are the number of correct items out of 15. So just double check 14, 13, 12, 11, 10, 13, 12, 11, 14, 10, 12, 12. Good. And then the no sleep group. Now, they don't have to have equal numbers in each group. They can, but there is no requirement that both these conditions have equal number of subjects. So these are our two conditions, sleep and no sleep. Now we want to find the sums of each column and we want to find the means and the degrees of freedom. So I'm going to sum up these columns. First column sums to 144. The second column sums to 108. So we're going to find the mean of the first group. So that's 144 over 12. So the mean of group 1 is 12. And we want to find the mean of the second group, which is 108 over 12. And 108 over 12 is going to be 9. So we have our two means. We have a mean of 12 and we have a mean of 9. We are then going to compute the degrees of freedom. So it's going to be n minus 1 for each group. So the first group is going to be 11, n minus 1, n is 12, and the second group is going to be 11. Degrees of freedom 2 is 11. So they're both 11 because they both have the same number of participants. Okay, now the variance. So since these are whole numbers, these are integers, I'm going to do deviation square method again. Because when I have integers, the deviation square method is just easier. If you have decimals, then you're going to want to do the x squared method. So let's do deviation scores first. For the sleep group, we're going to subtract 12 from each of these scores. Subtract 12 from each of these scores. Make sure this column adds up to 0, 3, 2, 0, 1, 0, 2, 0. And now we're going to square these. So we're going to have an x1 minus m1 squared column. These are the square deviation scores for sleep. And we're just going to square our deviation scores, getting rid of all those negatives. And then we're going to sum up this to get the sum of squares. 4, 5, 6, 10, 11, 12, 16, 20. So our first sum of squares is going to be 20 for this column. Then we're going to do the same thing with the no sleep group. Create a deviation score column. Subtract 9 from each of these scores. Make sure these add up to 0. -1, -2, -4, -1, -2, 0. Good. And now we're going to do the sum of the square deviation scores for our no sleep group. Just going to square these again. Add up these square deviation scores for no sleep. 1, 2, 6, 15, 16, 20. So our sum of squares for group 2 is 20. So our two sum of squares are 20 and 20. It's just a coincidence that they're the same. They don't have to be the same, it's just a coincidence. Now we're going to compute the pooled variance estimate. So our pooled variance estimate is going to be the sum of squares. Okay. Screen moves for a second. Sum of squares 1 plus sum of squares 2 over degrees of freedom 1 plus the degrees of freedom 2. Our two sum of squares are both 20, so it's 20 plus 20. Our degrees of freedom are n-1, so they're 11 and 11. So our pooled variance estimate is going to be 40 over 22. 40 over 22 gives us 1.82 as our pooled variance estimate. So we're going to take that pooled variance estimate and we're going to put it into the final t-score formula. So t is mean 1 minus mean 2 over square root of pooled variance estimate over n1 plus pooled variance estimate over n2. So our two means are going to be 12 and 9. And the denominator is going to be 1.82 for the pooled estimate. So 1.82 over 12 plus 1.82 over 12. Since there's a common denominator of 12 here, we can add. So this is going to be 1.82 and 1.82 is 3.64 over 12. And we're going to have to solve that. So 3.64 over 12. We go into R, which likes to shut off. And we're going to do 3.64 over 12. It's a little bit of a hiccup here for R to get rolling again. 3.64 divided by 12.303. So this is going to be the square root of 0.303. And that's going to be 3 over that square root. Point 550. And when I do that, I get approximately 5.45 as my t-value. That's a pretty big obtained t-value. So I'm feeling pretty confident that we're going to reject the null with this large of a t-value. Let's find the critical value. So we are asking for this hypothesis test, we're asking for the critical value at alpha of 0.01. So 0.01 alpha. Which is pretty low for alpha. And our degrees of freedom here are going to be 22. So we're going to have to find that critical value in the table that corresponds to 0.01. This is going to be two tails because we're looking at change. We're saying that the sleep group, sleep changes or affects memory. That is not a directional term. So affects memory means it could increase memory or decrease memory. So it's going to be non-directional and two tails. So we want two tails at 0.01 with degrees of freedom of 22. So we go into our table. We want proportion and two tails combined. We want the bottom row here. We want this to be 0.01, which is all the way to the right. And we're going to go down to 22. This right column, this bottom row, the second row, the right column, two-tail p-value, alpha value of 0.01. And the critical value is 2.819 plus and minus. So our critical value is plus and minus because it's two-tailed. So if it's two-tailed, you have to have a plus and a minus. You have two critical values for two-tailed. Plus and minus 2.819. And now we're going to compare our obtained value of 5.45 to that. But we're going to look at both tails. So our critical value in the negative tail is negative 2.819. And our critical value in the positive tail is 2.819. Our obtained value is way out here, 5.45. So since our obtained value is more extreme than our critical values, obtained is more extreme than critical, we are going to then reject the null. And we reject the null, we conclude that the sleep group, the sleep actually increased memory or changed memory, because we're looking at a non-directional. So sleep changes memory. And the way it changes memory is by increasing it. But since we tested the original hypothesis that sleep affects memory, we have to draw a more limited conclusion saying that sleep, affects memory in the affirmative. And then we can look at our data and say, yes, sleep increased the number of objects that the participants got correct in this delayed memory test. And that's how we do the independent samples t-test. We have two independent samples. They're not related at all. They are different people in each condition, each of the two conditions. We then find means and we find degrees of freedom. We then calculate pool variance and then plug into our t-test. And we use the t-distribution to find the critical values to test the hypothesis. And that's pretty much it. So hopefully that helps you. If you have questions, you can always email me. You can always ask me in class, come to office hours, etc. So bye for now. See you next week with more t-tests.